We have two speakers today, Rachel Hausco and Paula Cardenas Hernandez. They're going to talk about the research that they've been doing related to Project WiCCED. And so we're going to start with Rachel. Rachel is a postdoc in my group, in the coastal hydrogeology group. She received her PhD in ocean engineering from the MIT Woods Hole Oceanographic Institution Joint Program. And she is soon to start a faculty position at Penn State. She is working on understanding how Delaware's water resources will be affected by the changing coastal climate as part of Threat 1. So Rachel, go ahead and share your screen.
Thanks, Holly. I'm gonna try and Is that coming through? Okay, great. Okay, so thanks so much, everyone, for tuning in. So my work actually thinks about working on Project WiCCED as part of Threat 1 salinization, and I think about what happens to coastal aquifers after they've experienced these really big inundation events due to extreme storms that you could see here on the title slide. So this causes a threat to coastal freshwater resources. So here we're looking at a schematic of a coastal aquifer. And so inland groundwater is typically fresh. And then offshore, it's fairly salty. And so under calm conditions, what you get is a saltwater wedge that's driven by the density difference between fresh and salt water that sort of intrudes into this freshwater. But then when you have these big storms come through, it dramatically increases the shoreline water levels and inundates the coast with this ocean water. And then over time, that's going to start to infiltrate down into the aquifer system in a process that we call vertical saltwater system, vertical saltwater intrusion. And so after the storm comes through, this salt ends up being flushed out by discharging fresh groundwater. And so that's the process I'm really interested in understanding as part of Project WiCCED. And this salinization is important because it's going to threaten both the health of the eco-hydrological system and also limit the availability of fresh water for drinking, irrigation, and commercial uses in the coast. And so you can see kind of an example of that in these two images here. The image on the left is from the Virginia Long-Term Ecological Research Station, and the image in the top right is from one of the critical zone network sites here in Delaware. And in both of these images, you can see a lot of tree die-off, these white trees here. And the current hypothesis is that die-off is actually being driven by intrusion of this high salinity saltwater. So by being able to predict how systems respond and recover to storms, we might be able to better link that to what changes are happening in the ecology in these coastal zones. Additionally, Delaware is a very low-lying coastal state. So we end up, and it's also a very high agriculture industry area. So you have these farmland that's pumping from groundwater to irrigate crops right by the coast. So if you have salt water that makes its way into the aquifer in these coastal systems where you're relying on the groundwater, that could jeopardize your crop productions. And if you'd like to hear a lot more about the interplay between water use decision-making, groundwater pumping, and salinization, you should definitely tune in to hear Mary Hinks talk about those processes, I think in the December version of this seminar series. So a lot of studies have been done sort of thinking about these overwash-driven salinization processes that I'm interested in. Our group has done some work looking at repetitive storm surges in combination with sea level rise. There's been work looking at the permeability of the aquifer and how that might affect salinization, as well as different recharge and flushing schemes. And then there's been some work looking at the interplay between topography and salinization, but kind of the unifying approach to how these studies have been done is to model that storm surge as approximately a Gaussian pulse. So you can see that here in the bottom right, where you just have but in the surface water, those hydrodynamics are sometimes a lot more complicated. And so that's the piece that I'm really trying to tease apart through my work, is trying to understand how spatial variation in ocean surge profiles and also ocean hydrodynamics might affect the salinization and recovery of these aquifer systems. So right now I'm doing a lot of this work focused on the Delaware Inland Bays, which is this shallow bay system just south of the Delaware Bay on the coast. It's about 12 kilometers rise, and it's composed of two connected bays, Rehoboth Bay to the north and Indian River Bay to the south. And these bays are connected to the Atlantic Ocean through the Indian River Inlet. So the only way the ocean water and storm surge can make its way into the bay system is through this very, very narrow channel. And so that ends up being really important for how the hydrodynamics work in this system. So to look at the hydrodynamics part, I'm using output from a model called NEARCOM PVD that was developed by Dr. Fengyan Shi over in the CE department. And it simulates waves, currents, and surge of surface water. And I'm actually in my work only using the surge component of this model. It's run at about a 1 kilometer resolution. And so what I'm doing is taking output from this model, specifically for Hurricane Sandy in 2012, and then using that as boundary conditions for my coupled surface water groundwater modeling that you can see here. So I use a program called HydroGeosphere. If you're a modeler, what that does is it runs the St. Venant equations in the surface and the Richards equations in the subsurface. And if you're not a modeler, all you really need to do is this is the functionality that you need to be able to simulate exchanges between the surface and the subsurface and surface ponding that are important for these flooding and salinization processes. So in this demonstration model here on the right, the top, you're seeing the surface domain, and the blue is going to track the position of the ocean water along the land surface. And in the bottom, we're looking at the subsurface piece of the model, where the color indicates the salinity. So yellow is salty and blue is relatively fresh. So again, we have this sort of classical saltwater wedge at the beginning. And then as the ocean water level increases, you start to see high salinity water driven down into the bay. And then once that water level resides, that salt water starts to get flushed back out of the system. So as I mentioned previously, I'm using these outputs from the inland bays model, and I'm using two different grids to run this. So if the cell is indicated by a green circle, then it's going to overwash the inland section of the inland bays. And if it's water level that comes from a pink circle, then you're going to overwash a barrier grid. And I designed these sort of idealized cases based on the real topography of the inland bay system, as well as the previous hydraulic conductivities reported for the area. Okay, so now let's look at actually what happens during Hurricane Sandy in terms of surge distribution. So here are all of those points that I'm taking out of the model, and the color indicates the maximum surge level, where red is higher surges. So you can see that there's a really strong gradient in surge level between the ocean and the bay. So the barrier actually attenuates a lot of that surge energy, and you see the highest surge moving through this inlet. And that high surge level gets redistributed through the Indian River and Rehoboth Bays, where the Indian River surges are slightly higher. It's sort of hard to see the spatial variation. So now I've plotted the distribution of the surges relative to the mean bay and ocean level. So you see that there's not a lot of spatial variability in the maximum surge level outside the bay, but within the bay system, you do tend to see higher surges in the southern bay, Indian River, because that's more directly connected to that Indian River inlet, and slightly lower surges in Rehoboth. And then the last piece that I'm thinking about when I'm running these models is actually the tidal range. So you, very similarly to the magnitude of the storm surge, you tend to see higher tidal ranges here in Indian River Bay than you tend to see in Rehoboth in blue. So to run my models, what I've done is I've chosen 4 locations throughout this bay system for my inland runs that I think represent the range of surge levels that you see for this Hurricane Sandy storm event. And those are plotted as time series in the bottom right here, where the x-axis is time and the y-axis is the elevation of the water level during Hurricane Sandy. So you can see the thing that's actually driving the most variation across these profiles is actually the tidal range, which it has a much bigger variability than the actual maximum of the storm surge. And you can see that these profiles are a lot different than, again, that classical approach of applying a Gaussian boundary condition to run these overwash simulations. So if we look at what that actually means in terms of salt mass for the system over the course of the storm, you can see that here we're looking at time series of the added salt mass by the surge overwash as a function of time. And you can see that this, for the inland cases, these salt mass time series kind of followed the pattern of the boundary conditions. And there's not a lot of variability in the maximum salt that you see, but you do see earlier in time variations in the total salt mass in the system due to the variation in the tide. So I've gone ahead and done this again for the barrier cases, where I've selected 5 sites that represent the range of surge and tide values throughout the Rehoboth Bay system. And these are plotted on the figure on the right here. So we've got time on the x-axis and elevation on the y. And I'm using one single ocean level plotted by the black curve. And again, this really highlights the difference in surge levels if you stay inside and outside of the bay system. So barriers overwash a little bit differently than the inland case we looked at earlier, where you can inundate from both the ocean and the changes in the bay level. So we're going to see an example of one of these storm cases here. So you can see the tide moves up and back on both the ocean and the bay side. And then once you sort of start to overtop this berm on the bay side, you start to see salt water come through. But it's not until you get fairly close to the maximum surge levels of the storm do you start to see the bay level sort of inundate more consistently. So once those water levels start to drop back, there's a topographic low on the bay side of this island that does retain some water in the surface. And you can see the salt make its way down into the system. Because it's heavier, it starts to sink. And then once the storm has subsided, the salt is going to start to sink and then get flushed out of the system. Okay. So there's a couple things I'd like to point out about this. So because the bay side has lower topography, once it overwashes, you salinize a much wider region. But because the ocean levels are a lot higher, and this area of the coastline is inundated a lot more frequently, but saltwater makes it to a deeper depth on the ocean side of the island. So if again, we look at what that looks like in terms of the additional salt mass, we're now looking at salt mass on the y-axis and time on the x-axis. You can see that the profile with the highest tidal range in green actually gets the biggest salt mass because it starts to overtop the berm on the sound side of the island earlier in time, which results in more salt through the system. And if we actually run that out over a 10-year period post-storm, you can see that that higher salt actually gets retained over time. And you see something kind of interesting in this green profile where you see the salt start to get flushed, and then it starts to freshen again. And this is a dynamic that has been seen in some of Dr. Anair Powder's work, but you only see it for this green time series with where you had the most salt in the system. So it may be that you're hitting some sort of threshold salt mass where you're able to push that salt wedge more offshore and freshen the aquifer later in time when you have more salt enter the system. So it's possible that even these fairly small changes in the surface hydrodynamics will ultimately change the long-term responses of the system. So if we now look at the barrier and the inland cases together, something that's kind of interesting is that there was a 30-centimeter lower surge inland. But if we look at the amount of additional salt added over the course of the storm for the inland cases, which are the solid curves, and the barrier cases, which are the dashed lines here, you can see that the inland cases get a lot more salt. And that, I think, is a function of the topography. So for the inland cases, anytime you have a change in water level, whether that's driven by a tide or a surge, that's going to change the inland extent of the water level. But on the barrier case, the berm actually limits the surge extent. For a lot of the early times, you don't see a substantial increase in the salt until your water level is high enough really to overtop this berm. And then similarly on the ocean side, the dune is really functioning to limit the surge extent. The other thing I want to point out in contrast between these two profiles is that you don't really see the same mirroring of the boundary condition in the barrier profiles, and that's because the total salt that's being added into the system is a function of two different surge profiles acting jointly, the bay side and the ocean side, whereas on the inland profiles, you're looking at just one side of ocean inundation. The big caveat for this is the way that I've designed my inland grid is sort of representative of the mean slope near the bay, but the topography that you're seeing here is elevation, where brown colors are high elevation and blue colors are low elevation. Is actually pretty variable in the inland bay system. So there's channels and other topographic features that my model is not going to be representing well in the way that I'm doing this analysis. So in terms of next steps, right now I'm running NearCom with sort of surge only processes. And so I'm getting a little bit lower water levels than Feng Yang got when he ran the model, when he was using both waves, wind, and surge driving this model. So these are plotted on the same color scale. So you can see the levels in the bays that he's getting out of the model are higher than the levels of the bays that I'm currently using to run my groundwater models. And so some of my next steps are to add in more of these hydrodynamic forcings. I'm also interested in considering different storm cases. So Hurricane Sandy, because it was such a big event, you didn't see a lot of variability within the bay system in terms of what the maximum surge level was. But I think for more moderate storm cases where you aren't getting so much water through the inlet that you're able to elevate the water level in both bays, that variability in surge height might be more important. So here we're looking at the distribution of the mean surge height for two storms. On the left is Hurricane Sandy, which had about a 2-meter surge. And on the right is NearCom that I've run it for a nor'easter, which has about 1.5 meters surge. And you can see that there's a lot bigger gradient in the bay levels for this more moderate storm case. So I want to consider some different storm conditions as well in this analysis. And then finally, there's a lot of different spatial and temporal scales that you can think about these inundation processes in. So this is the model I'm using is run at about 1 kilometer, but there's a lot of variability in inundation and hydrodynamics that act at smaller scales. And you can see some of those here in the new 3-meter NearCom simulation that Feng Yan has built. And I think it would be really interesting to integrate some of those finer scale processes in the ways that we think about groundwater salinization and flooding as well. So to kind of take away from this is that salinization is pretty complicated. It's kind of a very complex interplay between the surface water hydrodynamics, the subsurface geology, which I didn't talk about a lot in the context of this talk, and the surface topography. And so that's something that our group is trying to think about modeling more regionally in a joint project with Dr. Anair Pelder and Ryan Fredericks in our group. So with that, thank you, and I hope I haven't gone too far over time. So.
Thanks, Rachel.
Okay.
We have their.
When everything was
Yeah, if everybody can mute, that'd be great. Thanks. Okay. Questions? Who has questions for Rachel? No questions?
Jeanette, I just wanted to, that was a great talk, Rachel. Thank you. And then the visuals were just so compelling. And I just found myself wondering, when you talk about, and I'm not even quite sure how to ask my question, so I'm just going to bumble through this one. But
That's great.
So when you talked about the salt being flushed out, right? But you just, at the end, you said it's salinization is complicated. So what does it take for the salt to be flushed out? And are there scenarios when it doesn't really flush out or?
Yeah, absolutely. So really what it takes for at least some of the salt to be flushed out is for your inland water levels to be higher than your ocean level. So that's going to drive a flow of fresh water that's over time slowly going to push the salt out. At the same time that that's sort of happening, the salt though is actually redistributing. So it's heavy, so it starts to sink down. And so that's going to change over time, like how it gets entrained into that freshwater flow and actually mechanistically how it moves out of the system. So I think so first of all, the residence time of any of these things is known to be sort of quite long. So at least on overwashes have been observed to still be salinizing them, almost a decade after the storm has passed through. So there are really long-term impacts of these events, and often not 100% of the salt does actually get pushed back out. So no, I think that's a good question.
Thank you.
Antoinette?
Hi, Rachel, that was a really good presentation. I really appreciate it. And just like Jeanette at the end where you said salinization is complicated, that made me start thinking about the research that I'm doing, looking at marsh grass salinity concentrations. So if your figures 34 and 35, where you have basically those gradients are not as gradient as I imagined, but you're showing something where you have, even within the same area, there can be a mix of high salt and low salt, which could have an impact that I didn't even realize was going on. So this really is an eye opener. So thank you. Thank you. This is a really good talk.
Oh, thank you so much, Antoinette. I appreciate it. Yeah.
Yeah, Antoinette, it would be fun to think about that, if it's relevant to your research.
Right, because I just did a real-time PCR and I was getting some wonky results, and this may actually, I might have to talk to you offline, Rachel, to see.
Yeah, definitely.
Your data. Okay, thank you. I'll reach out to you.
Antoinette, it could be cool too to think about the temporal aspect, because
Right.
storms is going to be saltier than, after rainfall.
Right. So that was one of the things that we tried to do, was not go sample after a rainfall, because we knew that that would have some effect on the salt levels wherever we were collecting from. So yes, definitely. Hopefully, are you going to Maine?
I'm not, unfortunately.
Rachel, will you be in Maine?
No.
Nobody's going. Okay.
We'll just have to, we'll have to find a time to get.
Yeah.
Okay.
Yeah, I'd be super interested to see your data and see like sort of where in the marsh you see those higher salinity values, because I think it could be connected to some of these inundation processes.
Okay.
Yeah, and really tiny changes in topography make a huge difference. Like the that Fagnon simulation that Rachel showed on those small scales, some areas get really salty and inundated, and others are just high enough that they don't.
Wow. Well, thank you.
Any other questions? Okay, if not, thanks, Rachel. Good timing. Excellent. Paula, you're up. So I'm happy to introduce Paula Cardenas Hernandez. She is a Colombian environmental engineer. She graduated from LaSalle University in 2016, and now she's a fifth-year PhD candidate in civil and environmental engineering at UD, and she's also a second-year Denon Fellow. She is working on contaminant transformation and environmental remediation, and developing predictive models for transformation of explosives in soils. Her results will not only have a practical application in contaminated sites, but also will help elucidate mechanisms and degradation pathways of legacy and newly developed explosives, thereby advancing our scientific understanding of the underlying processes that control the fate of these pollutants in the environment. And outside of her research, she's an Empower mentor. She helps first-year graduate students adjust to their new environment. And she serves as a volunteer in the Hispanic Latino Graduate Student Association, which creates a welcoming environment for the Latin community here at UD. So that's fantastic, Paula. Great to have you. I actually worked on explosives remediation as an undergrad for a summer. And so I'm
Oh.
super excited to hear your talk. So thanks, and feel free to share your screen.
Okay, thank you so much for the introduction. Let me share my screen. Mhm. Uh-oh.
Yeah, okay. That's good.
Good. Okay, so thank you, Holly, for the introduction, and thank you everyone for coming today. We are going to talk about contaminant transformation and a little bit of redox chemistry. So I will present my work, as Holly said, on how I am developing models that will help us to understand and predict how long is it going to take for an explosive to degrade in soils or in aquifers. But before we go there, I would like to say that by the end of the presentation, I would like to know why or how explosives get into the environment, why is it important to tackle this problem, and how we're trying to improve our understanding of this problem. All right, so let's start with how the explosives get into the environment. And it's just as any other anthropogenic contaminant, the explosives get into the environment during their production processes and also the testing. So just let me tell you, during the Second World War, there was a highly production of munition compounds or explosives. And at that time, there were, and still, there are not very good environmental regulations. And this led to the improper disposal of solid waste and wastewater that was not treated. The second way of how explosives tend to get into the environment is through the testing. So you can imagine these huge areas where the testing ranges, and they have to detonate explosives for testing the new explosives or training to train the new soldiers. And these combustion reactions, you will tend to think that they are complete. Once the explosive has detonated, it will go all the way to CO2, nitrogen gas, and water, but that is actually not the case. Very often they tend to be incomplete detonations. And when this happens, let me put my laser, I'm so sorry. When this happens, you can see something like in these two pictures. I hope you can see this pink color or powder on top of the soil, or this pink liquid. That is actually a tail inside of the TNT explosive. And when these explosives are on top of the soil, they can either stay there or migrate to the groundwater due to weathering. And this takes me to the routes of exposure of how humans are getting to this problem. So when this used to happen back in the 19th, the DOD started to monitor in these wells that were adjacent to the manufacturing plants and training ranges, because people started complaining because they were getting sick. The reason why is because they started to use this contaminated water that was that had explosives in it for drinking water and irrigation purposes. And some of the munition compounds or explosives are actually possible carcinogens, which makes this problem of importance. So once they realized this problem was happening, they wanted to know where the problem was happening, right? So this is a map of the United States, and as you can see, there are a lot of blue points. These blue points represent the contaminated sites, and as you can see, there is at least one per state. The red points represent the manufacturing plants, and the yellow points represent the training ranges. And there are some blue points that are overlapping nicely with the source, which means they are close to the training ranges or the manufacturing sites, but there are others that are not. And this is just a telling sign that there is contaminant transport through the subsurface, which is magnifying this problem. So the Department of Defense is starting to invest on cleaning solutions, environmental remediation solutions inside, but they also are starting to fund research projects that will help them to understand a little bit more of this project and speed up this transformation cleanup of explosives. So is there a cost-effective way to treat it? Well, the key in how to get rid of explosives is actually hidden in their structure. My research group focuses on redox chemistry, and this is the first thing we look at it at the molecules. So in here you can see I have highlighted in yellow circles a nitro group. This nitro group is highly oxidized, which is what makes it a good explosive. But this is also the weakness because these nitro groups are electron loving groups, as I like to call them. So they love to receive electrons, and this makes them susceptible to reduction transformation. So here in the bottom, I have this half reaction of a reduction of a nitro to an amine. And this reaction involves these 6 electrons and 6 protons. And we want to have, we want this to happen because once we have an amine, it means the reduction product could be less toxic, or it can be further mineralized by microbes. In this case of amine, they tend to be a little bit more toxic than nitro compounds, but they can be further mineralized by microbes, which is a good thing. Second thing is that this happens in the environment. In the subsurface, there are a lot of reducing environments that could transform these munition compounds to amines. So understanding this process will improve these cleanup processes. Can we accelerate these? Can we know how or what is actually reducing the transformation rates? I also wanted to mention that many anthropogenic contaminants like dyes and pesticides contain a nitrofunctional group, which may imply that some of the results from this research could be applied to other anthropogenic contaminants. Okay, so we were talking about nitric compounds need electrons to be transformed. So let's think about in the subsurface, what can donate electrons, right? And this is in my project, we like to call these soils geobatteries. And these geobatteries, sometimes they are charged with electrons, and is what I was just talking before. They can basically transform the explosives to their amino counterpart without no problem because there is enough reduced environment. But sometimes that is not the case, and we have our battery completely empty, right? So as environmental engineers, what we do in the environment, in the field, we use reducing agents so that we can harness this capacity of the soil to degrade contaminants. Here I have an example of dithionite, a reducing agent. And basically we use this reducing agent to donate the electrons to the soil. So we are charging this battery in the soil so that it can be further used for the reduction of contaminants like explosives. So once in contact with explosives, the electrons that are in the soil will be able to transform to a counterpart that we want to hit, which is the reduced explosive in here. So now that we know that, and now that we know that this can happen in the environment, the approach that we are using in my group is to divide the geobatteries that are present in the soil into multiple batteries. We think that the most predominant geobatteries in the soil that could help solve this problem are iron-based or carbon-based. And in my case, I am focusing in the iron-based part. How are we approaching to this problem? Well, we have an experimental component and a modeling component. And when I say modeling, I feel a little bit embarrassed because I just saw Rachel's presentation and it's like a highly modeling base. But in my case, I just try to relate the experimental component with thermodynamics and is using these linear free energy relationships. So this LIFR, as we call it, is a bridge that is bridging kinetics of reduction or the transformation rates and the thermodynamics. And so kinetics is how fast is the reaction, right? And we are changing pH, iron-2 concentrations, iron long leads, and explosives. And I'm going to explain this in the next slide. But for thermodynamics, we're just basically measuring is this going to happen or not, depending on the thermodynamics of the system. For this, we have two parameters that will help us to predict this. The first one is the reduction potential. For those that are not familiar with this term, it just means how reduced this battery is. The second one is the first electron reduction potential. And for those that are also not familiar, it means how reducible the explosive is, how willing to receive the electrons, right? So to explain a little bit more these two parameters, I wanted to show a illustration. So the more negative the reduction potential or the P is, the stronger the reductant. And the more positive the first electron reduction potential is, the molecule will tend to create more electrons, right? So this is for the reducing system or the soil or the iron oxide. And this one will be unique to the explosive, right? But what happens when the explosive doesn't want to be reduced? So I see redox relationships as human relationships. When you are not willing to accept anything, you are just not going to accept it. And in this case, she didn't want to accept the flowers. So just imagine a munition compound that has a low or a more negative first electron reduction potential. It wouldn't like to receive electrons because it's reduced enough, right? So the idea is that the more negative the P, the better. And the more positive the first electron reduction potential, the faster the kinetics. Okay. So this is the geobattery that I focus on, is iron oxides and iron 2. And these two, when iron oxide get reduced to iron 2 partially, they create a redox couple that can be illustrated here in this half reaction. And in this plot, I wanted to show you how remember, reduction potential is how reduced the system is. Well, how the reducing state of this geobattery can be affected by increasing the iron concentration and also increasing the pH. So these are two very important variables that will help us to speed up or slow down the reaction. Okay, how do I do my experiments? In my case, I don't look at big systems. I tend to do lab or bench experiments. So you would imagine a reactor in which I will spike hematite. I will buffer the pH because, as you saw, the pH is very important for controlling the kinetics of the reaction. I'll add the iron 2 because I just show you they form a couple. So it's important to have hematite and iron 2 together so that iron 2 would be able to react, because iron 2 by itself is not a very good reducing agent. And then we'll add the NaCs or MCs. MCs, I forgot to mention, is just a short for munition compounds. So I'll sometimes use explosives or munition compounds or MCs. So once we have this, we'll track the reaction over time. And we'll do this with an HPLC. We'll track the explosive concentration or the MC concentration, and we'll track the iron 2 concentration over time. Then what we do is calculate using the Nernst equations what the reduction potential of the system will be at a given pH and at a given iron 2 concentrations. Once we have this, we'll be able to use that to model the kinetics of multiple NACs and MCs at different reduction states. So these are my results. I wanted to show you the first part of the problem is how reduce the geobattery. We first need to know how the reduction potential of the system is affecting their kinetics. In here we have a lever because, as you remember, the levers relate kinetics with thermodynamics, right? So kinetics are what I measure in my reactors that I just showed you, the rates. And in here in the x-axis, we have the minus pH plus P, which is just pH plus the reduction potential, which is how reduced the geobattery is, right? What you can observe in here is that we have multiple explosives, right? At different conditions. So we have 1 millimolar iron 2 and 10 millimolar iron 2. And as you can see, they form different, they form or they follow the same slope, right? You can see it, they follow a similar slope, but the intercept is different, right? So the implications of this is that first, they may react in the same way, regardless of their structure, because if you remember in one of the first slides, all of them have nitro groups, but they have different instructions. Some of them are nitro aromatic, some of them are heterocyclic or nitramides. So the difference in their structure did not affect this model or how this model could predict the reactivity. But this is only specific to the MC. They don't form a single line. So this is a lever for each specific MC. But the importance is that the slope is similar regardless of their structure, so we can use an extra parameter that will help us to predict in a better way the reactivity of these MCs, right? And that parameter, as I just explained in the previous slides, is how reducible the explosive is. Is this munition compound or explosive willing to receive those flowers that I just showed in the illustration? So as you can see, these kinetics are faster, and this is because 4-cyanonitrobenzene is more willing to receive electrons than RDX, right? And they also follow trends. You can see trends with the similar slope. These are at a given pH plus P, which is like this one, the one in the x-axis. So the thermodynamic state of the system is influencing each of the intercepts, but the slope is the same because these were conducted at a similar pH plus P. So this just implies that if we put these two together, if we put how reducing the geobattery is, or if we also include how reducible the explosive is, we'll be able to create a model that will help us to predict how long is it going to take for each explosive to be degraded by, in this case, hematite coupled to iron 2, right? The importance of this is that this is not only distinct for hematite, it can be applied to goethite. So in here, we have in the red markers, we have hematite. And the importance of this work is that they are present in soils, right? So what do we do for soil? For soils, I cannot calculate the reduction potential because there is not such Nash equation, right? So what we do is to measure the reduction potential of the system in the lab. We took soil samples, we measure them in the lab. We use mediated potentiometry because to get reproducible results, mediators sometimes are needed. And I have highlighted in here in blue some zones in the in the plot because in the x-axis is the extent, right? Extent of reduction. And this extent of reduction is just a way of estimating how much of this reducing agent, remember dithionite, when you don't have electrons, you have to add it. So how much of the reducing agent you need to add to get an enough negative reduction potential to be able to degrade contaminants. And in this case, this is the range where I could observe good reaction or rates that I could track over a day. So as you can see in here, this is the first step. We have to measure how reduced the geobattery is. We then need to use the reported values of how reducible the explosive is. And once we have these two with, of course, the kinetics, we'll be able to generate a lever. This is so exciting. You don't know how long we have spent to try to get these results. And here we have the reduction rate constants versus the lever, which is the how reduced the system is and how reducible the explosive will be. In here we have 4 soils and multiple explosives. The fact that they follow between the boundaries of the lever is just as exciting as going to an Adele concert. It's like the fact that you are able to predict the reactivity of NACs and MCs that are different in their structure in a complex system like soil can lead to a better understanding on how the iron content, the iron content of the soils could lead us to a good prediction or of the interactions between the munition compounds and the soil. So I have the takeaways, and you can use this in case of an emergency. If you have a happy hour this Friday, you can let them know that you know that iron is an important geobattery and that this one can be used for explosives transformation. We have this biggest system, which is the soil. I am focusing in a more detailed one, but the fact that soils were, I was able to model the kinetics of explosives in the soils using the same approach that I did for the iron oxides implies that this is a highly applicable technique. The fact that we are also able to take two thermodynamics parameters, the one for the reductant or the reducing system and the one for the oxidant, implies that we'll have a success of applying this lever of this model for my more complex systems. I forgot to mention that for the soils that I use in this study, they are mostly ferruginous. They have a high content of iron. So for next, for the future or near future, I'll try to explore a little bit how the organic content could affect the reactivity of these munition compounds. For acknowledgements, I would like to thank my professors, Dr. DiToro, Dr. Allen, Dr. Carbonara, and Dr. Xu, and also the postdocs of my lab, Dr. Murillo and Dr. Hickey, and my lab mate Juan. Also, the accountants or our research group for keeping me sane during the PhD, and my funding agency, Serioes, Denny, and EPSCoR. Thank you so much.
Thank you, Paula, for your presentation. Does anybody have any questions for Paula? Jeanette, please go ahead.
Yeah. Hi, Paula. Great talk. Thanks so much. And I loved your analogies too. Holly wrote a little note that she loved the analogies. So the, accepting the flowers, and it was great. But I was just curious about what was the most surprising thing? You've been doing this for a few years. And was there something that was really surprising to you over the course of your work that you didn't expect to happen, or something that you learned that was encouraging?
So the reduction measurements for soil, remember how reduced the soil is? That is a measurement that I know Danielle does here in her field, but we have so much trouble with it to it in the lab. We spent like almost 2 years trying to develop a technique or a methodology that will help us to do it. Because what happens is we are measuring the reduction state in a metastable state. So we have just reduced the soil with the reducing agent, right? We added the electrons, but that soil is there to react. So it's not like an stable, the thermodynamic stable state. And the fact that it worked for multiple soils, we were just amazed. Like that final plot, I almost cried when I got it because it's ferruginous mainly. So we haven't explored how organic carbon can affect the kinetics, but soils are just so complex. And the fact that it worked is the most surprising thing, because after failing so much, we thought we wouldn't be able to make it.
So you really persevered for that one.
Yes.
That's good.
Other questions?
Can I have another question?
Well, Rachel raised her hand.
Rachel's next. Rachel's next. Sorry.
Hi, Paula. Really, really nice talk. And I apologize if you said this and I missed it, but what is sort of the time scale of this sort of soil battery process? And like, how does that relate to thinking about timescales of persistence of this in sort of a natural system? You're trying to translate your lab stuff into
To the field.
yeah.
So I think if we were to translate it to the field, we'll have to take into account the transport component,
Okay.
Which is something we are not taking into account just yet. In the lab, depending on the explosive, we'll have different rates because some are more reducible than others. The newly developed explosives by the Department of Defense, I think at circumneutral pH, they are gone between minutes.
Oh, wow, that's
Uh,
really quick.
The problem are the legacy ones, RDX, TNT, RDX, nitroglycerin. They are less reactive,
Okay,
and therefore those are still in. They were generated like a long time ago, like since Second World War, but they are still there because they don't just react too slow.
great, awesome. That answers my question. Thank you.
Thank you.
Okay, Jeanette, go ahead, please.
I kind of had well, it's sort of a similar question. I was also very impressed by the map at the very beginning to show how pervasive, the contamination is. And also, suggesting, you were saying, like, I was noticing, like, here's one blue dot all by itself. So, and the fact that suggests that it's being transported to that location, right? And
Yeah.
so globally speaking, is this is a very could you talk a little bit about kind of the global nature of this problem?
Oh, yes. So I could talk about my country actually. In Colombia, I am from Colombia, and we have this internal war for 50 years. And for this war, we had a lot of landmines in Colombia. And due to weathering, they have been exposed for more than 50 years, but we don't have the actual techniques to test how much or what is the concentration of explosives. So that is a way of saying countries that have war, for sure this is happening. But also, I get almost every country in this planet has a military, and they have to train them, and they have to also test if the explosives are working or not. So this military contamination by explosives is basically global, but also we use explosives for constructions and for mining. So the application of these munition campaigns, it's funded by the Department of Defense, but I think it has a wide application for other industries too. And I hope that the tools that I was using, they are very easy to use. Is something that you can measure in the environment too. Danielle is doing it. So I think this can help like third world countries like mine to be able to know when to degrade these contaminants, because what they are doing right now is extracting the soil and putting it in a facility, or combusting, or like pump and treat. These are very inconvenient things, very cost effective. So only first world countries like United States could do it, but ours not. So yes.
Thank you, Paula. Any other questions? Okay, well, I want to thank both you, Paula, and Rachel, for presenting today. You both did a lovely job. Thank you very much for telling us about your research, and good luck continuing. And we really appreciate your time. Thank you, everybody, for being here today. Have a good afternoon.
You.
Thank you. Bye-bye.